Now that rate law, actually that rate equation is often proportional to the some power of the reactants. It can be also proportional to some integral power or fractional power of the products also, and then we can define the order of the reaction. However, if we cannot write it in terms of a simple equation like where the overall rate equation or the rate is proportional to the product of concentration terms, and each term is raised to some integral or fractional power, then the order does not have any meaning. And today we'll see that we gave an example that how the reaction between, very simple reaction between hydrogen and bromine, which apparently seems to be a bimolecular reaction, but actually it is a very complicated reaction. It's a overall composite reaction which is composed of many elementary reactions, and then we see a very complicated expression for the rate, where not only the reactants come into the rate law, concentration of the reactants, but also the products come into the rate law. So today we'll discuss that mechanism as well as a few other reactions, mechanism of few other reactions, and we'll see how to devise a mechanism successfully so that it satisfied the overall rate law which is experimentally observed. Now to begin with, let us first define what is an elementary reaction. So by the name, as the name suggests, you can ask this question: why all of a sudden a molecule is forming a product? It must be some energized molecule, and meaning that we had a molecule, and that due to thermal heating, which means heating means always collision with other molecules, or by some other activation, say for example by shining light on it, it can actually go to some higher excited state, and then we call it as an energized molecule, and that energized molecule can give rise to product. And then the rate for elementary reactions, we can always write it as the reaction is written, I mean in the stoichiometric or the balanced equation. So we can write it like K into A, because this is a fundamental step. And for a bimolecular reaction, if it is something like more general type, A plus B going into product, so the rate will be equal to K into A into B. Now elementary reactions are always unimolecular or bimolecular, because the probability of having more than two molecules collide simultaneously and giving a product will be very low. Usually in gas phase or liquid phase, the collisions which we observe are dominated by bimolecular collisions. So this kind of reaction, if we find that we have three species and giving rise to some product, then we cannot say that it is elementary, and we cannot also write it as A into B into C. This is actually wrong, because it must be then a composite reaction which can be broken into elementary, bimolecular as well as unimolecular reactions. Now, so elementary reactions are always classified as unimolecular and bimolecular reactions. Now we'll discuss both of these together, but first we'll start with the bimolecular reaction. So we have two components, A and B, and giving rise to some product. And for unimolecular reactions, we have a model, we have a kinetic model that also we'll discuss today. Now the first thing is, let us take an example, like the nitrogen dioxide example we yesterday discussed, the formation of nitrogen dioxide from nitric oxide and oxygen, and this actually formed nitrogen dioxide with some rate constant, and that rate constant I am writing at K suffix OBS. OBS means actually it's an observed rate constant. So K OBS is observed, or better to write it as experimentally observed rate constant. Experimentally observed rate constant. Now the question is how the rate law for this reaction will look like. The rate law we found that also was experimentally determined, which we can write it as formation of in terms of nitrogen dioxide formation, dNO2 dt, or we can also could also write it in terms of the concentration of nitric oxide or oxygen with a negative sign, and each time we write it, the coefficient or the stoichiometric coefficient will come in the denominator, and the negative sign will come for the reactants, while positive sign will be considered for the products. Now that we found that it follows a rate law like this, and as we said that three body collisions are rare, so this is not an elementary reaction where two nitric oxide molecules and one oxygen molecule collided simultaneously at the same time to produce the product, which is nitrogen dioxide. It must be broken into smaller steps, which now we are going to discuss. Now the first mechanism we are going to, by the way, the mechanisms can be of one particular reaction can have very different mechanism, and each mechanism, of course, by mechanism we mean that each mechanism or each model actually satisfactorily explains this observed rate law, because this is what we are getting experimentally, and we have to explain, or we have to get at the end of the day an expression for which actually matches the experimentally observed rate law. Now let us consider an model. So that first model says that in the first step, nitric oxide gas and oxygen gas reacts in a bimolecular reaction, and that is forms nitrogen dioxide. Now if you see the equation, the stoichiometric equation, NO3 doesn't come into picture, so Na3 must be a reaction intermediate which you do not observe. And in the second step, this nitrogen trioxide gas reacts further with nitric oxide to form two molecules of nitrogen dioxide. They are all gas phase species. So we divided the entire reaction, which is a composite reaction, which is expressed by this stoichiometric, this reaction which has perfect chemical stoichiometry. But we are saying now this reaction can be broken into two elementary reactions. Each of them is bimolecular elementary reaction, and in the first case, first reaction, we considered a very fast equilibrium between the reactants and the products. So it's a reversible reaction, the first one, and the second one is actually a slow reaction. Now if you have many elementary reactions happening together, the overall rate will of course be dependent on the slowest reaction. Now we can have an analogy. For example, suppose you have many lanes and where cars are going on road, and then there is a bottleneck, and then you can easily judge that the overall speed of the cars, or the average speed, will be actually dominated by the speed of the slowest moving cars, because they are creating the bottleneck in the road. So in the similar way, the slow, if it is a slow reaction, or the slowest step of in a composite reaction, so that reaction will control the overall rate. So the overall rate will be determined by the slowest rate step, or that particular elementary reaction that has the that occurs at the slowest speed. So that step we call it as rate determining step, because it determines the overall rate. It's a determining step. Now let us consider how will we devise a mechanism. Also consider that we have some rate constant for this forward reaction of the first process, and as well as a reverse reaction, and the second reaction rate constant I'm writing as K2. So considering the first equilibrium, we can always write that there is some equilibrium constant. I'm just writing K equilibrium suffix 1 to denote that it is a first reaction, first elementary step, and for that we can write it as, this is nothing but NO3 divided by NO divided by O2. So this is from the first reaction. Now the overall rate of the reaction, as we said, will be controlled by the rate determining step, and you can see actually the NO2 is formed in this step. So the formation of NO2, if you just consider the second reaction, so the rate will be given by rate of the second reaction, which is dNO2 dt, which is actually the rate of the overall reaction. So you can see the overall reaction rate is controlled by the slowest step, is, according to the second equation, is K2 times NO3 times NO. But we know that NO3 can now be replaced by this. And this equilibrium constant, remember, is nothing but the ratio of the forward rate constant divided by reverse rate constant for step 1. So you can right away actually replace the NO3 concentration by this particular expression which we just got. So it will be K2. Instead of NO3, we are writing it as K1 by K minus 1 multiplied by NO into O2 so that is for NO3, and it was then multiplied by NO. So you can easily rearrange it. You can see that it will be nothing but K1 by K, K1 K2 by K minus 1 into NO square into oxygen. So you can see the rate law now satisfactorily describes the observed rate law, where we discovered that this K observed is nothing but a combination of rate constants of elementary step, and this is the expression for K observed. So this is a mechanism which satisfactorily explained our observed rate law, which is actually some rate constant times the nitric oxide concentration squared times the oxygen concentration, and we found we can satisfactorily explain. However, we still do not know whether this mechanism is correct or not. You can actually come up with something and some model and which satisfactorily explains it. Now remember that here the assumption is that the NO3 actually is formed as an intermediate nitrogen dioxide. So in order to demonstrate that okay, your model is correct or not, you have to show that this nitrogen dioxide NO3 is a species that was generated. Now you can actually do some experiments which are called reactive intermediate trapping experiments, because usually these intermediates will be very short-lived. They're formed and then and there they react, because they will be very reactive to form the product. So this intermediate, sometimes you can actually go to very low temperature, freeze the collision momentarily, and then or trap it in a matrix, and then you can actually do some spectroscopy which actually will tell you whether this species NO3 is present in your mixture or not. If you can identify yes, NO3 is present in this mixture, then actually it supports this mechanism. I'll show that there is another mechanism that we can propose for this reaction that also satisfactorily describes this reaction. Now point number 2 here is that we learned one interesting thing, and composite reaction can be broken into elementary steps, and this is one way of breaking a composite reaction into elementary step, where we considered first equilibrium in the first step, and then there is a slow rate determining step. So overall this kind of mechanism is known as a rate determining step or RDS approximation. So we just what we just did is proposing a mechanism based on this RDS approximation or rate determining step approximation. We'll now consider the other approximation. So this is nothing but RDS approximation, or the rate determining step approximation, where we approximated the or constructed a model based on the approximation that there is a slow step which is the rate determining for the overall reaction. Now similarly we can propose another mechanism, which is known as steady state approximation. Now already we discussed in the previous lecture what is the steady state concentration of the intermediate. If you remember that we considered a consecutive reaction of the type A is going to B and going to C with some rate constant K1 and K2, and we showed that under the condition K2 much greater than K1, the concentration of B reaches a steady state concentration, which is basically remains constant over time after some period, which is known as the induction period. Now we'll consider a slightly different version of this, in the sense that we're explaining the same reaction, 2NO gas plus oxygen giving rise to 2NO2, and then we'll consider the steps in a slightly different manner. We'll say that okay, fine, there is a nitrogen gas, and first the two nitric oxide gas react together to form N2O2. Now you see that there is a different species here, so that is step 1, and then this N2O2 reacts with oxygen to form two molecules of nitrogen dioxide. Now stoichiometrically this is fine. If I just add 1 and 2, that is also giving rise to the same thing. But here I'm not considering an equilibrium step in the first case, and what we are trying to say here is that we have a rate, and then we have basically two reactions. So let us first compare with this equation. So if you write it in this way, now you can see that I have a similar situation where I have to approximate that this concentration of this intermediate, which is N2O2, is actually has reached the steady state concentration after some time, which means I'll approximate this change. Steady state means the concentration is almost constant, will be almost equal to 0. So we have to just find first a rate law for the intermediate concentration and then put it 0, and then we are done. However, in this model we'll slightly modify it a little bit. So we'll say that actually there was an equilibrium, because just we are keeping an analogy with the earlier case where we said that there is a first equilibrium exist and there is a slow rate determining step. Here we are considering a slightly different thing. We are considering that okay, yeah, there is an equilibrium and there is a irreversible step, but we'll solve it in a different way, and we are solving it under the assumption that the N2O2 concentration doesn't change over time, and we'll figure out if there is an equilibrium, what is the condition. Just like if there is a irreversible step, this was the condition, K2 is much greater than K1. In this case we'll see what is the condition. There's a striking difference here. Here you see that it is one species going into another species, but here actually there is a bimolecular reaction going into some species. So there is a slight change between this steady state approximation and this steady state approximation, which we are right now discussing. This steady state approximation is actually for a bimolecular reaction. Now let us proceed. So what we will write is that dN2O2 dt, that should be 0, and let us try to figure out where actually the N2O2 is being formed and being consumed. Now look at the first step. So it is being formed from two nitric oxide molecules, so we can write it that it is K1 into NO square. But in the first step, the reverse of the first step, it is actually destroying. So it is destroying at a rate of K minus 1 into N2O2 concentration, just the reverse step. And then again it is destroyed at a rate in the second step. So destroying means we are writing negative sign because it is being consumed. It will be K2 N2O2 into oxygen. Now we can just arrange terms. This is 0, so you can readily figure out what is the N2O2 concentration. The N2O2 concentration will be, you can see it here, so N2O2 appears here, N2O2 appears here, so it will be K1 into NO concentration square divided by K minus 1 plus K2 into O2. So the rate of the reaction, which is d NO2 dt with the half sign, that you can see that the second step is the step where this NO2 is being formed. So the rate of the reaction is the rate of the second step, which is nothing but K2 into N2O2 into oxygen. And if we just replace the N2O2 concentration by the expression what we just derived based on the steady state approximation, is that, so this is under steady state, that should be 0. So then we get, it is K2 K1 into NO square divided by K minus 1 plus K2 into O2. Now you see that we have not discovered the observed rate law. We have to make a further assumption. Now what is this assumption? Now think about it. Once I form this N2O2, its concentration, it's an intermediate, and we approximated that its concentration is steady state. That's why we made it 0. Now the question is, what are the conditions that made this steady state to be valid? Meaning, if I form something, the intermediate, that should immediately disappear. Something like for the irreversible case, we said that as soon as B forms from A to B, so then immediately it converts to C. That should be that steady state, that will lead to the steady state condition, which means K2 has to be much, much larger than K1. Now, in order to understand that, let us think that, okay, fine, how N2O2 is can be disappeared. So N2O2 can be disappeared. How N2O2 is formed, basically in the first, think about it. So N2O2 is actually disappearing like this, like the reverse of this reaction. So the reverse of the first step, we can write it K minus 1 into N2O2, and then there is another step which is taking it forward, which is basically K2 into N2O2 into oxygen. Now this is basically rate of step minus 1. Minus 1 means the reverse of the step 1, and this is rate of step 2, which is the step 2, which is just a forward reaction. So the N2O2 is formed, and then it can actually go back immediately to the reactant, or actually it can immediately go to product. Now think about it. If it immediately goes into the product, then we have a problem, because then the product formation will be extremely fast. So then we have an inconsistency, but we know that the product formation is not extremely fast. So what we can do here is that we can make that as soon as N2O2 is formed, it actually goes back to the original state. And so that way we can also make the N2O2 concentration as a steady state. Instead of saying that the N2O2 is formed, that is, and it is immediately forming the product, we are saying no, actually N2O2 is formed and it immediately goes back. Because if that the other condition is true, then the product formation rate will be extremely fast. So that is not the situation. So we are saying that this rate of the reverse reaction of the first step is much higher than the second step. And of course, the rate of formation of N2O2, that is also much lower. I mean, there is a forward step K1, it is forming, and immediately it is going back. So that's what we are saying. Now, if we impose that condition, you can divide both sides by N2O2. So you are saying that K minus 1 is much, much greater than K2 into O2. Now, we can use this condition now into here, and then we figure out that the d2O2 dt will be nothing but K2 K1 into NO square divided by K minus 1. We assume that K minus 1 is much greater than K2 into O2. So now we see that the observed rate law is the same like before. There will be oxygen also. We missed the oxygen here. Yeah, so we just replaced it by N2O2 concentration, and we wrote it like that. Yeah, so we just replaced the N2O2 by the steady state concentration, which is here, and there was a K2 times there was a oxygen. So this is the, yeah, this is the K2 and this is the oxygen. So we see at the end of the day, this is the same rate law which we got from rate determining step approximation. However, the striking difference, there are two. The intermediates are different. So in one case, intermediate was NO3, nitrogen trioxide, and in the other case, it is basically N2O2. Now, there should be some chemical or physical logic behind choosing rate determining step for one reaction involving one particular intermediate, and steady state approximation for the other reaction which contain another intermediate. Now N2O2, nitrous oxide, it is basically dinitrogen dioxide or something like that. N2O2 is a very reactive species. So the assumption here is that we do not see actually N2O2 in that medium. So then what we are saying that N2O2, as it is formed, it immediately decomposes into NO and two NOs basically. Okay, so that's why the logic is something like that. Now you can ask this question: if you take these two steps and apply rate determining step approximation, or if you go back and take this mechanism and apply the steady state approximation, what do you get? You can actually work it out and see how you can recover the similar rate law. So you work it out by yourself and see whether you are actually getting the same or similar rate law, and also you are getting the observed rate constant as a combination of these rate constant, which is K2, K1 by K minus 1, which are actually rate constant for the elementary steps. Now, to summarize, we just choose only one particular reaction, and we showed that how you can actually start from you can very cleverly use these two approximation. One is a rate determining step approximation, where there is a first equilibrium followed by an slow rate determining step, and the second one is where actually you have an intermediate, but over time the intermediate concentration doesn't change. That is known as the steady state approximation. And if you make either of these approximations, then you can actually show that yes, you can actually get back your old equation, I mean the observed rate law, which is experimentally observed, and then you can write the experimentally observed rate constant as a combination of all your old rate constant. Now remember that we gave you this example of this rate of this reaction, and showed that although the rate law shows that it is a very simple straightforward thing, that two nitric oxide molecules and one oxygen, and then it is giving NO square and O2, but we showed that actually the inherent mechanism of this reaction is very, very different. It involves various intermediates. It can actually in this particular case, to the best of my knowledge, this reaction can proceed through either of these mechanisms. So both mechanisms happen in parallel for this particular reaction, and both mechanisms are correct, and both mechanisms actually satisfactorily explain the observed rate law. So in the following section, we'll start with another reaction mechanism, and where we'll use the steady state approximation more extensively.